So if you are watching this, you are sick or not in class. I'm going to be doing video notes for probably now on for the rest of the year. So in our case, let's just get started. We're gonna do 5.1 today, which is angles. No, it is angles. Angles of triangles. That is what we are learning today. Yeah. So this, the notes that I'm doing right now, you should have the copy of it. I should have a blank copy on Google Classroom and a filled out one already on Google Classroom, but you need to watch this first. I am writing everything down. I do not have a copy of the notes as I am recording this. And I probably want to write it down fully anyways because that's just how I like writing in general. But follow along. Everything I fill out on this paper is what you have on your fill-in note sheet. And just to be warning you right now, I currently only have 3 colors that I'm working with, maybe 4. We have a colored pencil on my desk, but I only have 3, so you're going to be seeing black, blue, and red a lot until I go out shopping this weekend. So let's just get started with 5.1, which is angles of triangles, with classifying some triangles that we already know about in math in general. So we're going to be classifying triangles right now by sides. And what I mean by this is that when we start thinking of triangles, I'm going to draw a few right now and we're going to work off of them. There are some distinct features that these triangles have with each other, and they all have unique names. Now, this is actually kind of a bad one. So we are going to just scribble it out. It's not what I want, actually. I want something more like this. I think this one looks better. It's gonna make the point of what I'm trying to make easily. So this triangle, I'm not gonna add anything to it. This triangle, I'm gonna add some markings right here. And this triangle, I'm gonna add markings right here. Now, these 3 have very different features that they're working with. Notice that these marks that I made, we know what these marks are already in math class. They're congruent marks, which means that sides like this one and this one are the same. They're the same length. And also with this triangle, all 3 of the sides that make the triangle are the same. So that's a good thing to know when we start classifying triangles. And we can state each one has like its own name. With this one, the one that has no congruent sides, that is I picked the worst kind of blue for this. It's a scalene triangle. And scalene triangles have no congruent sides. Notice how there's no markings on this triangle. No congruent sides, not allowed. On this one, we have 2 congruent markings. In that case, this is actually called an isosceles triangle. And this has 2 congruent sides. And lastly, we have an equilateral triangle. And this has 3 congruent sides. So all the sides on this triangle is the same. So that's a good thing to know. But these are 3 classifications of triangles that you can make when we only talk about the sides. Now, there's different other classifications you can make about triangles, and that dives in more with the angles that are inside of these triangles. So there are 4 classifications that we can make with triangles by their angles. So we're going to state all those now. So classifying triangles by angles is the next section. And one thing you can notice, take a gander at what we have up here, and just don't even think about like the actual, like, don't worry about the blue text right now. Just look at the actual triangles. What do you notice about the angles that all of these have? The one that should be popping in your head is acute angles. So there are things called acute triangles, and that is one of them. God, just throw pens around. So this is an acute triangle, and notice that an acute triangle, like a lot of these ones up here, it has 3 acute angles. So to be an acute triangle, you have to have 3 acute angles. So keep that in mind as we keep going. There's 3 other ones that we are going to talk about. The next one, if we're already starting talking about acute angles, you should kind of start thinking like, oh, what are the other kind of angles that I know of already? The one that should come to mind easily is, and is probably the most famous triangle, the right triangle. Throwing pens. The right triangle. And for a right triangle, to classify it as a right triangle, it has a right angle. Has right angle. So a right triangle has a right angle. So that's how you can classify that one. The next one, if we're still going on the angle scheme of like knowing like, oh, we have an acute triangle, we have a right triangle. The next one that should come to mind is the obtuse triangle. And this triangle is defined by having one obtuse angle. So notice that with the acute triangle, we have 3 acute angles. The right triangle only has 1 right angle, and then the obtuse triangle only has 1 obtuse angle. So those are 3 classifications for classified triangles. There's one more, and it kind of dives into one of these triangles up here that we have talked about already, and that is the equal angular triangle. So I'm going to try to draw this one as best as I can. So this is the it's not equal angular. It's equilateral triangle. Whoopsie. Equilateral triangle. And this has 3 congruent angles. You can see it by the congruent markings that it has already. I'm going to color them in so it's like a little better looking. But it has congruent markings on the triangle itself. So you can call it an equilateral triangle, has 3 congruent angles. One thing to note about an equilateral triangle is the fact that this is also an acute triangle, because you'll understand it more later, but this is the same as this, technically, but it couldn't go in the other way. Like an acute triangle cannot be equilateral. It doesn't happen like every time. It's like, it's almost if and only if, but not really. It can go one way, but not the other. Note on all of this is the fact that you can combine the classifications together. What do I mean by this? That means that I could take like one of these triangles, like scalene and obtuse. I can combine those to make like a scalene obtuse triangle. It doesn't work for all of the triangles, but you can do it for some cases. Like one of them that we will be doing is, for example, 1. We are going to draw an obtuse isosceles triangle. So looking at what we have up here, the obtuse triangle looks like this. Isosceles, remember, has two congruent sides, so we have to put the marks there. So that means we need to draw a flat triangle, not a flat triangle. We have to draw an obtuse angle, and that these two sides have to be the same, equal the same. They will have the same length. So that means I have to add the tick marks up here, and even you could gauge it at that point. Like, yeah, this is an obtuse angle, and we have the two congruent sides, so that covers our obtuse isosceles. So we combine two of the classifications together to make a triangle. Now, one thing before we move on is the fact of like understanding how you can get these congruent sides. We know how to do this already on finding lengths of objects, of finding figures. In this case, we have done it before, and it was all the way in Unit 1, and we kind of did it again in Unit 3, where we are given a figure, and we need to find the distance of certain things. So what I'm talking about is that if we are given these congruent sides, and we want to find the length. So finding length, we are going to use the distance formula. So recall the distance formula, remembering it. We have the square root of y2 minus y1 squared plus... No, I was about to put a square root inside of a square root. Holy crap, we're not doing that. X2 minus x1 squared. All under the square root. Remember the distance formula, that we're using it again, by the way. And we'll be using it for the next example, actually. So we are going to take this paper and move it out of the way. So we are going to work on the next one. So example 2. We are going to classify our triangle ABC by its sides. Then we shall determine whether it's a right angle or not. So you'll be given problems like this and to work with. First thing to note, I'm going to give the vertices out for A, B, and C. So A is 0, 3. And we have B, which is 7, 1. And C, which is 1, negative 1. If you have the fill-in sheet... if you have the guided notes, you should have an actual figure of this. I do not. I get to draw it. Lucky me. So I'm going to make the figure itself. We're going to try our best to be artistic, I guess. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, that should work. It's going to be good enough. All right, A, we are at 0, 3. A, B, 7, 1. And C, 1, negative 1. All right, draw this in. So I need to classify this triangle by its sides. How am I going to classify the triangle by its sides? What did I just do on the previous page? I said that if we're going to be classifying triangles by its sides, we got to use the distance formula. Before we move on, you guys better write out what lengths you're working with. I'm doing AB, I'll be doing AC, and I'll be doing CB. I'm finding the lengths of those figures. So what I want you guys to do is to write out each one. I want you to write AB, AC, CB. Do not assume lengths. You cannot count. Do not count it. I don't care if it's flat. Like if you have one going this way, like if you have a line going this way, or if it's going like up and down, use the distance formula. You're not going to count. Use the distance formula. You need to practice with that. So we're going to use the length of AB. And yes, it's going to be a little monotonous, but do not assume. Please do not assume. So we got to do the distance formula 3 times. Sorry, buddies. So we got AB first, which is 7, 1, and 0, 3. So I'm going to do 1 minus 3 squared plus 7 minus 0 squared, giving us negative 2 squared plus 7 squared, giving me 4 plus 49, which is the square root of 53. I'm not going to simplify it. I'm going to keep it in the square roots because it's just going to be easier for me. I'll write the next one in black just so it's not red on red on red. So we got AC now, which is the square root of, I'm going to do negative 1 minus 3 squared plus 1 minus 0 squared, and that's going to give us the square root of negative 1 minus 3, which is negative 4 squared plus 1 squared equals negative 4 squared is 16 plus 1, which is the square root of 17. Make sure you're make sure if you're using your calculator to use parentheses while you work with negative numbers like this, because if you didn't have the parentheses around this negative 4, it would end up being negative 16, which is wrong, because then you'd end up with like negative 15 over here and you can't have a negative square root. Make sure you're using your parentheses. CB is our last one that we have to work with. We have the square root of negative 1 minus 1 squared plus 1 minus 7 squared. That's going to give us negative 2 squared. I hear my dog upstairs right now. Here's a picture of my dog. He's very cute. And then, oh, I lost track. I'm sorry. We zoned out. 1 minus 7. Negative 6 squared. And then we square root simplify first. We have 4 plus 36, giving us the square root of 40. Did we do everything right? Yes, we did. All right, so notice we're going to have to compare everything now because that's just the stage we are at. So we have the square root of 53, the square root of 7, and the square root of 40. Notice that none of these are the same length. So if we look back and reference our previous sheet, looking at the side lengths, equilateral says it has to have 3 congruent sides, which means, remember, congruency, equal, same thing. So do we have 3 equal sides here? No, we do not. Do we have 2 equal sides here? No, we do not. So that means that this is a scalene triangle. Good to know. So this is a scalene triangle. So I can write that triangle ABC is scalene. But this is not our final answer. Remember that... Did I even spell that right? I did. Okay, good. This is not our final answer because that's only part 1. We also need to determine whether it's a right angle or not. This is the beauty of doing notes on videos, that I can fix whatever I want. I didn't explain doing this part good, so I'm going to do it again. So I have to figure out if this triangle ABC is a right angle. We found that it is a scalene triangle. I'll write it back down here. Triangle ABC is scalene. This is part 1 of our answer. We need to find part 2, which is finding out that it is a right angle. You cannot assume anything. Do not assume anything you see. So even if this right here looks like a right triangle, even if this looks like a right triangle, you cannot assume it is a right triangle. So when I see your guys' work, like you did with the distance stuff, I want to see each one drawn out Like, I want you guys to do the distance formula for each segment for a triangle. I want you, if it's asking to determine a right triangle, if you need to see if it's a right triangle, if you to find a right triangle, you have to find the slope of each line. You have to. I am not going to. I will be so angry. You have to give me the slope for each angle or each line, because you cannot assume anything that you see, even if this looks like a right angle. It may or may not be. You are not going to assume. Don't assume. You're going to find the right angle for each one, or find the slope for each one so you can compare to find a right angle. Now, remember, when finding a right angle, what can we do when that involves like intersecting? Remember, if we have intersecting lines, two intersecting lines to make right angles, have to be perpendicular with each other. Remember this from each other. Remember that from Unit 3 with perpendicular lines. If we have two lines that are perpendicular to each other, they create a right angle. My dog is squeaking his toy. So if we remember this fact right here, that means that we have to have slopes that are opposite reciprocals of each other. I'm going to spell reciprocal wrong. I'm sorry. There we go. Each other. We spelled it right. Anyways, what does that mean? Example. Let's say we have line 1. It has an M of 4. And let's say line 2 has an M that is 1 over negative 4. These two are opposite reciprocals of each other. And you can check that by doing 4 times negative 1 over 4. And remembering the rules that we had when we did do parallels, to figure out if these are opposite reciprocals and they create a right angle, if you multiply them together, you'll get negative 1. So that's what we're trying to see. And we're going to do the slope, finding the slope for each one of these segments. And remember, finding slope, we'll do that. y2 minus y1 over x2 minus x1. And that gives us our slope. Remember that. Going down. We got to cram this one in. All right, so let's find AC first. Why am I doing AC first? I did AB first last time. All right, AC. We have negative 1 minus 3 over 1 minus 0, giving us negative 4 over 1, which is just negative 4. AB, that is 1 minus 3 over 7 minus 0, giving us negative 2 over 7. Dude, my dog's going crazy. He has his toy. We call it Blue Bear. Oh my god. Is that going crazy right now? Holy crap. Alright. Anyways, CB, this is the last one we have to do. Notice that these two are opposite reciprocals, so we can say AC intersecting AB, no right angle. All right, last one, negative 1 minus 1 over 1 minus 7. That gives us negative 2 over negative 6, giving me 1 over 3. Okay, so looking at my slopes, I can tell you right now that if we look at these two for AC and CB. That is this intersection right here, which is the one that looks like the right angle. They are not opposite reciprocals of each other. They're close, but they're not, which is why we can't assume. This is 1/3, this is -4. If we times them together, they do not equal -1, so that's a no-no. -2/7 and 1/3. That's AB and CB. So this intersection right here, not a right angle. And then what is the last one? This one, I think, doesn't work. We went over that one already. Not a right angle. So for our final answer, triangle ABC is a scalene triangle with no right angle. That's our final answer. Next section is finding angle measures of triangles. So when the sides of a polygon are extended, other angles are formed. So what this means is, like, if we have a triangle that looks like this, let's just call it ABC. When we extend the sides of this triangle, just think of it as like it's shooting out almost like this. Like these sides are extending outwards. That's what this stated. That's what it is stating. Now, when we have angles that extend out, when we have the lines of this triangle extend out, we create two different kinds of angles. One of those angles is an interior angle, and the second one is an exterior angle. So when we look at an interior angle, drawing it as so, boom, 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 CBA, always label, please. Interior angles are the angles inside of the triangle. That's an interior angle. So this is an interior angle. All of these angles inside of these triangles, interior. Every angle inside of a triangle is interior. It doesn't have to just be a triangle. Any angle inside of a figure, of a polygon, will be an interior angle. Exterior, getting out my pens. Exterior we have A, B, C. It is the angles on the outside. So like these angles. This would be exterior. Angles on the outside. And keynote about exterior angles. They form a linear pair with the interior angles. So that means, like, if I draw out my interior angle right here, this would form 180 degrees. The exterior plus the interior gives me 180. Remember this for exterior. Interior, everything is inside. All of these angles, interior. That's what's inside of the shape. Exterior, the ones on the outside. That forms from the lines that we extend, and that they are a linear pair with the interior angles on the inside. Note this part right here. Remember this. Look, see? We have the exterior right next to the interior. Sum that all up together to get 180 degrees. Remember it. All right, next. I should probably move that out of the way so I can look at stuff. All right. So next thing is one of our theorems that we're learning, and it's actually very important, and it kind of proves a little statement I said earlier on equilateral triangles. So it is theorem 5.1, which is the triangle sum theorem. The triangle sum theorem is the sum of the measures of the interior angles is 180 degrees. What does this mean? So I'm going to draw out a triangle. It's as good as it's going to get for right now. We have A, B, and C. Those are my angles of interest. So let's just say on the inside, I have this angle right here, and it's going to be different from B, and it's going to be different from C. One thing that I can say because of this theorem right here is the fact that our measurement of angle 1 plus our measurement of angle B, I said angle 1 instead of A. The measurement of A plus the measurement of B plus the measurement of angle C is going to equal 180 degrees. This is true for all triangles. So, going back to this, fun fact about this triangle, if we have 3 congruent angles on the inside of an equilateral triangle, that means that this triangle right here, each angle will always be 60 degrees by theorem 5.1. What we just did there was proving that statement with our theorem. That's how proofs can go sometimes. With that, you just prove that statement. With that theorem, you prove the statement. Good job. Keep that in mind. That's a good fun fact. So next one is another theorem. This being, that was our last proof, by the way. We're not doing any more proofs today. Theorem 5.2, which is the exterior angle theorem. This states that the measure of an exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. What does this mean? You might be asking. Say I have this triangle right here. We have C, B, and A right here. And let's just say I have angle 1 right here. So, the measurement of the exterior angle. Remember what exterior angles look like? It's the ones on the outside. So, the measurement of angle 1 is congruent to the angles that are non-adjacent to it. So, remember adjacent, that means right next to it. So that means that angle A and angle B will be equal to 1. Not angle C. No, bad. No angle C. But angle A and angle B, yes, we like that. So that means the measurement of angle A plus the measurement of angle B will equal the measurement of angle 1. No C. No angle C. I'd circle that one for you guys. Do not use angle C. It's the ones that are not next to it. So if you see one here, A and B. If we had an angle right here, like an exterior angle right here, it would be B and C. If we had one up here, it would be A and C. So if it's next to C, use the other ones. Like, this is a good picture. I draw this. Circle the ones that you use. Write no on the one next to your exterior angle. I'd just write no next to your exterior angle to help you out. Or not your exterior, next to your, yeah, just write it next to it. Right like this. Do it this so you know that you are not using C at all. We're going to do a problem like this. Example 3 at this point. All right. So we are going to find the measurement of PQS, and I'm going to be given this figure right here. On the inside, we have, I'm missing, I haven't even drew like the whole figure yet. Hold on, P, and then we have Q, S, and R. For P, well, for this spot right here, I'm going to put 3x plus 25. I'll have 2x. I'll have 65 right here. And notice that we don't have anything in Q. So first thing I'm going to do, what my theorem says, we are not using the angle right next to the exterior angle. I know I don't have anything here, but I'm going to write no here. If I had an angle here, I would cross it out, scribble it out, put big X, red X on it. Do not use it. In our case, we don't have it, but I'm writing no here. We don't mess around with that angle at all. So if we apply our theorem up here, it would be our measurement of angle R plus our measurement of angle S is equal to 3x plus 25. In that case, that's the measurement of PQS. So that means we'd have 2x plus 65 equals 3x plus 25. And this is just the case of simplifying. So I will do minus 2x to get 65 equals x plus 25. Minus 25s on each side, giving us x equals 40. We have x equals 40. That means I can plug in x into 3x plus 25 to get my angle for PQS. So I have now 3 times 40 plus 25. That's going to give me 120 plus 25, giving me 145 degrees for the measurement of PQS. Really recommend just writing no right next to the exterior angle, just so you know you don't have to mess around with anything. So before we move on to the last thing today, we are going to write out something that I don't think you guys have seen yet, and it is a corollary. Oh, guys, trust me, I have not learned how to say this word, and I've known it for like 5 years. Corollary. Oh. So what is this? It is a statement that can be easily proven by using a theorem. We did this already, kind of. Is very informal. This could be a corollary. We could write it into like a real statement, like an equilateral triangle will always have 60-degree angles, and that would be a corollary. We're not going to officially write it like that, but that's a very informal one. But we are going to write one for theorem 5.1. So a corollary for 5.1, and it states that the acute angles of a right triangle is always complementary. And if we draw out a right angle, we can notice that, well, remember, I'm not even on. The triangle right here, it's already 90 degrees. Like this is 90 because we have that symbol right here. And remember the insides of this is 180. So let's just call this C, call it B, call it A. So we have our measurement of angle A plus measurement of angle B plus measurement of angle C equals 180 degrees. So A plus B plus 90 equals 180. And that will lead us to the ending of the measurement of A plus the measurement of B equals 90. Subtract the 90 on both sides. That's a very informal proof, but that's what this statement is saying to us. We're going to have a little example on it. It's going to be a little more wordy problem-esque, but it's the last example for you today. So example 4 is a word problem. I'll write it all out. So we have the measurement. The measure of one acute angle of a right triangle is 1.5 times the measure of the other acute angle. Find the measure of each angle. So key things to note from this is the fact that we have acute angles and that we're dealing with a right triangle, and one angle is 1.5 times the other angle. So when we start writing this out, let's think of it as a situation of we have two angles that we don't know the values of. So let's say we have X and X. This is angle 1. We're just going to label as angle 1. This is angle 2. We know that one of these angles is 1.5 times bigger than the other angle. So I have angle 1 and angle 2. For one of these x's, I'm going to write 1.5 right next to it, because now this angle is going to be 1.5 times bigger than this. Okay, now that we know that we're working with a right triangle, remember what we just wrote out too? Like the fact that this is the thing that we work with. A plus B equals 90. And if we're working with a right triangle, this process happens to make this true. We can put this into an equation. So we'll have x plus 1.5x equals 90. We can solve for x at this point. Combine my x's, so I'll have 2.5x equals 90. Divide 2.5. That'll give me x equals 36. That's one of my angles. That's my angle 1 up here. Now I need to find the other angle. So I'll first write angle 1 equals 36 degrees. Angle 2, I don't know yet. So that just means I have to plug in my x into this up here. So I'd have 1.5 equal 1.5 times 36, giving me 54. So angle 1 is 36 degrees. Angle 2 is 54. I could add it all up together. So 36 plus 54, that does equal 90 degrees. So that means these two angles are my correct answer. The homework assignment should be on Google Classroom, and it is now currently 7:42 at night. I am going to go eat some yogurt and eat a bagel. I hope you guys enjoyed, and I will see you tomorrow. Have a good night.